everyone. My name is Elena Pfeiffer. I'm coordinator of International Excellence Grants and a Fellowships Program at the International Scholars and Welcome Authors of Karlsruhe Institute of Technology. It is an honor to welcome you today to the third edition of the International Excellence Talk Series at KIT, which we are organizing together with the Humboldt Regional Group, Karlsruhe Pforzheim. I'm now particularly glad to hand over the floor and the screen for welcome and opening remarks to Professor Dr. Thomas Hirt, Vice President for Innovation and International Affairs of KIT. Professor Thomas Hirt is much more than solely the project owner of the International Excellence Grants and Fellowships Program. He is one of the inspirers of this talk series, and he is also an indefatigable supporter of internationality at all levels. Ladies and gentlemen, please welcome the opening remarks of Vice President Professor Thomas Hirt.
Good afternoon, ladies and gentlemen, dear scientists, doctoral candidates, students, dear colleagues. It is a great honor and pleasure for me to welcome you to the third International Excellence Talk. This new lecture series was initiated in May this year, and it is designed to provide a platform to present and to discuss the current research topics of internationally renowned scientists in an interdisciplinary context. I'm happy to see that the two previous talks inspired a broad audience and encourage a lively exchange of ideas. KIT is one of 11 universities of excellence in Germany selected in the year 2019. And our concept, the Research University and the Helmholtz Association Living the Change, includes 3 lines. First, to enhance performance and agility of top-level research. Second, to develop awareness of responsibility. And third, to increase the attractiveness for excellent young scientists. This will be achieved, among others, by strengthening international collaboration and promoting interdisciplinary networking between research communities. That is why KIT established the International Excellence Grants and Fellowships Program, which makes it possible for researchers at KIT to invite outstanding international colleagues to perform joint research. This instrument is flexible and intended to further intensify international collaboration of KIT with top-level universities and research institutions and support researchers from both KIT and abroad to continue existing and to initiate new scientific partnerships, especially projects in the time of the COVID-19 pandemic. Meanwhile, we have already initiated 3 nomination rounds for international excellence fellowships, and 20 researchers have been selected to be awarded as International Excellence Fellowships of KIT. 8 of the 20 researchers are women. Some research days have already taken place despite the pandemic, and we are delighted to host 3 International Excellence Fellows who are at the moment at KIT. Today, I'm very happy to introduce as speaker Professor Antonina Pirrotta from Università degli Studi di Palermo from Italy, the first woman to be awarded for the American Society of Civil Engineers Fellowship. Un caloroso benvenuto da parte mia al KIT, Professoressa Pirrotta. Professor Pirrotta's research stay at KIT is part of her long-lasting collaboration with a group of Professor Carsten Poppe at the Institute of Engineering Mechanics of KIT. In her talk, Professor Pirrotta will give insights on the topic of virtual experiments, why and how, and many thanks for this. In these times when researchers cannot meet face-to-face, we make use of virtual forms of dialogue. And I'm convinced that this new event series can make a useful contribution to a better understanding of most relevant research topics, promoting interdisciplinary exchange, as well as underlining the importance of international collaboration and exchange of ideas. An important goal of our new format is to initiate new contexts and collaborations and research ideas. Many thanks to Elena Pfeiffer and Petra Roth for organizing today's event and the KIT International Excellent Fellows Program. Now I would like to hand over to Professor Carsten Proppe from the Institute of Engineering Mechanics at KIT. Professor Proppe is the academic host of Professor Pirrotta during her research stay at the KIT. And he will give a short overview of the academic career of Professor Pirrotta and briefly introduce some highlights from the successful cooperation. At the end, I would like to thank you all for your participation and the interest, and I wish you all the best for today's event with an interesting talk and discussion, and please stay safe and healthy. Thank you very much for your attention, and dear colleague Professor Proppe, we are glad to have you as host, like you at KIT. The screen is yours.
Thank you very much, Professor Hirt, for the opening words. And let me say that I'm really grateful for the opportunity to invite Antonina Pirrotta within the program of International Excellence Fellowship. Let me start with some personal words on my first meeting with Antonina Pirrotta. And well, when everything started, it was a little bit a story about how we did not meet, because it was in 1995 already when I received an award for my graduate studies in both mathematics and engineering. It was a kind of travel grant, a sum of money that I would only get if I spent some time abroad. And at that time, I decided to go to Italy for 3 months while doing my PhD thesis. And why to Italy? Because there was a golden generation, I would say, of scientists in Italy in the field of computational stochastic mechanics that Antonina, you will very well know. Professor Augusti, Professor Borri, Professor Casciati, and I think I will stop with the letter D, Professor Di Paola in Palermo, which was a supervisor of your doctoral thesis. And unfortunately, during these unforgettable days in Palermo, I didn't meet with Antonina because she was a doctoral student, but she was also abroad. Namely, she worked together with Professor Ibrahim at Wayne State University, and Professor Ibrahim you can see on the right photo, right of Antonina Pirrotta. And when she came then to Innsbruck, where I was a postdoc with Professor Schueller, I already moved away from Innsbruck. So it was our shared predilection for the computational stochastic mechanics conference series that eventually brought us together. And that was a conference series that has been organized by Professor Spanas, and you can see on the photo, Professor Spanas to the right of Antonina, to the left you can see Professor Di Paola. And Professor Spanas organized that conference series since 1991, and it takes place every 4 years on a Greek island. And this event is as important for us, I would say, as the Olympic Games. So these are the Olympic Games in our field of research. Let's move to the next slide. And there you can see Professor Antonina Pirrotta with her group. And she has published since now more than 250 publications. She has made a large number of contributions to the development of stochastic structural dynamics. And the focus of her first contributions were on non-Gaussian excitation. That was the field of research where we basically met. Her publications on nonlinear systems under various kinds of non-Gaussian excitations, including Poisson-White noise and Levy processes, mark a milestone in this field. Then she advanced another completely new field in structural dynamics, namely the fractional calculus for modeling viscous and non-local behavior, especially damping behavior of structures. She did not only develop the theory and the solution methods, but she also contributed to the identification and experimental validation of non-local models based on fractional calculus. For structural analysis, she invented the line elementless method, a truly mesh-free method, you could say kind of Trefts method. that allows to solve boundary value problems for structural members efficiently and without any mesh discretization. And moreover, Professor Pirrotta has made significant contribution to structural identification, to structural control, and to structural health monitor. She holds not only a position of full professor at the University of Palermo now, but she is also a honorary professor at the University of Liverpool and is a visiting professor all over the world. She serves as Vice Dean of the newly created Engineering Department, and she is a member of the Scientific Council of her university, the University of Palermo. She has participated and coordinated more than 50 funded research projects, both on the national and European level. She is a brilliant organizer of conferences, especially in Italy, and at very nice places, I have to say. And she served for the scientific community in editorial boards, advisory boards, and organizing committees. On the next slide, you can see here during the award of the EASD Senior Research Prize for her outstanding and continuous contributions to the development of methodologies for structural dynamics. Unfortunately, it was again a virtual event. And she is the first European woman that has been awarded the ASCE European Engineering Mechanics Institute Fellowship. And this is a very prestigious award. She's the second person in Italy that has been awarded this fellowship and the first European woman. And today, Professor Pirrotta will give a talk about virtual experiments, a subject she is involved in for many years. Virtual experiments tend to replace more and more on-site experiments, either fully or at least partially. And I am very happy that such a brilliant scientist like Professor Pirrotta will share today her insights with us on this important subject. Antonina, the floor is yours. Thank you very much.
Thank you, Professor Prof. Thank you, Elena. Thank you, Anna. And thank you, Professor Thomas here to invite me and for this kind invitation that I really appreciate. I will be very grateful to you forever. And thank you, Professor Prof, for these nice words. Hopefully, well, they said, I'm not sure, by the way. The key point of my talk today is to stress the importance of virtual experiment, especially in scientific field. Well, for our society, and no matter where do you live, if you live in Germany or in Italy, in Russia, Japan, no matter at all, wherever you live, you have this problem. You have to predict the real phenomenon and to face this phenomenon, of course. And to do that, we have to underline the modeling and the simulation in all contexts, especially in, for instance, in structural design, in transportation design, why not? And also in mechanical engineering design, and even in the medical problem, in the medical context for biomechanics, and also for vibration control. That is my passion. So here you see the real world, and here you see the mathematics. But what joins both these worlds is just the experimental test. However, to run an experimental test is very expensive, not only because of the equipment, because you have here this, for instance, a shake table to simulate ground motion and other equipment to record the signal. They are very expensive, but also to run an experiment, it costs. It costs material, persons, a lot of costs. So the experiment, by the way, is a step of the scientific method. Well, let me show you what is a scientific method. The steps of a scientific method are characterization, that are observations, hypothesis, that is the theoretical part, predictions, that is the reasoning, and for so far, we just have the same step for defining a mathematical model. But now we have experiments. Experiments make the difference between a mathematical model and method and the scientific method. But I hope with all my heart that in the future, another step will be added, that is a virtual experiment. A virtual experiment is this. Efficient experiments allow to build up virtual experiments. Once a proposed theoretical formulation is reliable, having confirmed efficient tests, then simulations from this mathematical formulation are virtual experiments, but we will see later also. Virtual experiments, they are very a challenging problem because they are important in all contexts I already defined. And also, the most challenging problem is just to join Leonardo da Vinci and Feynman. Leonardo da Vinci that thinks that those who fall in love with practice without science are like helmsman who enters a ship without a rudder or compass, who is never sure where to go. Leonardo da Vinci stresses the importance of the theoretical part, but Feynman, the Nobel Prize, says it doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. So maybe virtual experiment can join them. Leonardo da Vinci, theoretical part, and Feynman, the experimental part. So let me talk about my experience in vibration control. That is, I already said, my passion. And I want to confess, to share with you an opinion. I want to confess something. Well, when talking about a medical problem, medical field, we say that is amazing, that is weird, that is full of mystery. When talking about engineering problem, somebody can think that it's more straight, more direct, and I don't say easy, but more straight, without mystery. But it's not in this way. Believe me, in the engineering field, we have a lot of mystery. Look, for instance, think about the strength of shape. You have here a sheet of paper, then you see this, it doesn't take even own weight. But if you do this, then you can add some weight. It will resist. So this is just for the strength of shape. And for me, it's amazing. It is, of course, in engineering field. And another amazing thing is the game of frequencies. In the game of frequencies, finally, I will destroy a myth. I don't know if you think, for instance, if you live here, that is the Teatro Massimo in Palermo, my hometown. So if you live here, since it is a huge structure, you are safe, you feel safe. And if you live here, that is a slender structure, this is a skyscraper in Dubai, maybe you don't feel safe. And this is totally wrong, because this is not a matter, safety in this field, in engineering field, it's not a matter of robustness of the structure, but it's a matter of several things. Well, if we have to talk about some dynamics, let me just give you some few words. No, I promise you, I don't go into details, into massive details, but just let me show you that is a static force. That means statics. It doesn't depend on your time. It's constant, for instance, forever. And dynamic load is depending on your time, is changing with your time. So here you are, you have this. And since it's changing with your time, then you can talk about a own frequency. For instance, here you have this sinusoidal force. This is F naught, is the amplitude of the force, the maximum amplitude, and the frequency in hertz is the number of cycles per second. So Look, here you have, this is one cycle, this is another cycle, 3 and 4 cycles in 4 seconds. So your frequency is just 1 hertz. And then you have a period. This is the period that is the inverse of the frequency in seconds. That is the time necessary to complete one cycle. And you don't have to think that frequency is a matter of a force or an external force. No way. Frequency, any system has a known frequency. I have my frequency, you have your frequency. Look, I bought this bird here in Karlsruhe just to show you. Look, this is the bird I put here. The bird is quiet, doesn't move. Then I change his position and then I release. See, the bird goes up and down. So it starts vibrating. And if it vibrates, he has a own frequency. A own frequency, it doesn't depend on the external world. These are like a free vibration because we don't have an external force. It depends on the geometry and on his material. And he has this frequency, up and down. Then, for instance, I saw also this. This is our ladybug. Ladybug goes back and forward, so he has their own frequency. Marienkäfer, I know that is a name. So Marienkäfer has a known frequency, and also the flowers. Everything is oscillating as own frequency. I have my own frequency. And look, this is strange. I don't know what is that. I really don't know. And also, you don't know. He doesn't know me. I don't know him. But I know that he has an own frequency. So now let's start about playing with these frequencies. In which sense? Let me show you. You have this system, and you say that the system has an own frequency, as you already know. So say this frequency is omega 1. Then you have an earthquake. This is a ground motion. And the ground motion as an own frequency is a dynamic force. So it's an it has a own frequency, say omega 2. Then if the system and the earthquake have different frequencies, the system could be damaged, but it doesn't collapse. It will remain standing. While if the system and the excitation, the earthquake, are the same frequency, then you see here, you have larger displacement, as you see, than before. This phenomenon is called resonance. And this phenomenon can lead to collapse because you have this so large displacement, so large vibration, and it's not, believe me, it is not a matter of amplitude. The amplitude is the same. So it's a matter of this game between the frequency of the old system and of the external system. So in this case, omega 1 on the left, omega 1 is different from omega 2, and on the right, omega 1 is equal to omega 2, so you will face this resonance phenomenon. And you have to face, otherwise you will have the collapse of structure. An icon of that, of this resonance, as you maybe already know, is a Tacoma Bridge. Tacoma Bridge was built in 1940. And you see here, Tacoma Bridge is a huge structure. It's very big structures. And at that time, it was after 4 months of this construction, it was new. At that time, a wind was forcing the bridge. The wind was having the same frequency of the natural frequency of the bridge. So then the bridge collapsed. And this is not a video game. This is a real story, as you already maybe know. So let's go back to virtual experiment. So to do a virtual experiment, of course, you have to run an experiment and a real experiment. So here you have, for instance, an experimental setup. This is the model. This is the shake table to simulate the ground motion. And this is the acquiring system. So you have a sensor in the head of the model, so you can record the signal response from this experimental test. And as I already told you, this is a quite expensive system. So let's go inside my lab at the University of Palermo. Just a quick view. This was the shake table, and this is another shake table and this model is mounted on the shake table. This is the acquiring system. And this is a very expensive, this is a laser vibrometer setup. So look, I have here the experimental test. And I run this experimental test and I put the sensor on the head here. So I record the signal response. And here I have this mathematical model. This is a second order differential equation, and this is the excitation that I have. I am not going into detail, but the mathematicians, they know how to solve this. And look, I solved this second order differential equation, and I put in this graph. As you can see here, you have both experimental from the solution of this equation, and you have the numerical from the solution of this equation, and the experimental signal from the recorded signal of the experimental test. And they are overlapping each other. So they match very much. So they match very much. And so you cannot say that you have a different, this is a question and the real world. You have in this way a virtual experiment. That's really amazing, because you see here, experimental test, numerical simulation, they are the same. So for me, this experimental test is the same. To see here, this equation of motion is like that you have a circle and you have x squared plus y squared equal to r squared, that is the radius. So for me and for you, it's the same. So this is the real world, and this is the mathematical model. But now the real world is an equation, and an equation is a real world. So they are the same. That's the meaning and the importance of the virtual experiment. So we talk about resonance phenomenon. So let me just show you some experience on that to face a little bit this problem. To face this problem, you have to control the system. And there is a passive control. You have a device. You have to put a device to control vibrations in resonance. So you have here the main system. And here is the equation of motion, the mathematical model. And you put here a pendulum, like you put in your structure a pendulum with a mass. Here you are. And since here you have two systems, you have two frequencies. One is of the main structures, and the other one is of this, that is called the tuned mass damper. And we have to tune both frequencies. They must be equal. Omega 1, the main, is equal to the system of tuned mass damper. And this is the question of motion of this controlled system. There are several applications. The most important one is the type A 101. And here you have inside this huge pendulum with a huge mass, iron mass, that is like 600 tons. Then you have also Hancock Tower Boston, and you have a Citicorp building in New York. And now we can consider another kind of device, that is the tuned liquid column damper. That is, you replace the mass of the pendulum with this U-tube shaped, and you put inside this tube, you put inside just water. And so you have this device that is called the tuned liquid column damper. Also in this case, you have to tune both frequencies, the frequencies of the tuned liquid column damper and the frequency of the main system. So this is the mathematical model, but is the mathematical model, take care about that I found in literature, the classical formulation, we say. Also in this case, we have some applications. Is more recently the other one, the tuned mass damper, but also in this case, we have real applications. Like in this case is One World Center in Vancouver, and this is a front view, and this is a top view. You have also Random House in New York, and here you have two devices, one in this direction and the other one in this direction. So let me show you something about the effectiveness of this control. I built up a model in my lab. This is the scale model, and this is the main model, because here you cannot see the liquid inside. So this is the main model, the uncontrolled model. And this is the controlled model with the tuned liquid column damper, because you can see here the liquid inside. So look at this video. We have three different models excited by the same excitation, same amplitude. And everything is in resonance, that is, the main system has the same frequency of the excitation. And so you can see here that we record in the head of the model, we record the signal. The black one is the signal of the uncontrolled system, that is the main system. The blue one is the system controlled by tuned liquid column damper. Here you are. And the red one is the best performing of this. And this is the system controlled by the tuned mass damper. As you can see here in the main, it moves a lot. The other controlled systems, they don't move. It's the control device that's moving. It's just the system with the tuned mass damper is moving. And also the liquid inside is moving, as you can see here. See, the main is moving with a lot of large vibrations. Tuned mass damper is just, it doesn't move. It moves only the pendulum inside, and in the control system with the tuned liquid column damper is the liquid that moves more than of course, the performance is better for the tuned mass damper. But by the way, the tuned liquid column damper is more easy to tune, also to build up, and also to maintain. This is the experimental setup that I already showed you. By the way, this is the shake table to simulate ground motion. This is the model. This is the sensor to record the signal. And this is the acquiring system data. So now, look at these results. This is the mathematical model, the classical one. And these are results, experimental results versus numerical results. And there is no match. So I was feeling frustrated because you cannot say that you have a virtual experiment in this case. So I think, well, maybe I changed something about the frequency. No way, look, I feel frustrated. Here, I changed the frequency. No way, much frustrated. So even intermezzo acceleration, it looks a little bit better, but not perfect. So I cannot say that the classical formulation could be a virtual experiment. But if you see here, the comparison between the experimental results and the numerical results for the tuned mass damper, here you have good results, always experimental, match, and overlap the numerical one. So in the tuned mass damper case, you have a virtual experiment, but no way for the tuned liquid column damper. So look, frustration, because here is the match for tuned mass damper, everything is perfect, and this is for tuned liquid column damper. I change also the frequency. Here, perfect, tuned mass damper, and tuned liquid column damper. In this case, is a little bit, but it's not perfect. Look, frustrated. I feel very frustrated. Tuned mass damper, changing once again the frequency. Tuned mass damper is perfect, and this is not perfect. No way to match. So I was looking better this formulation. I am not going into mathematical detail, but I like to show you something physical that is the most important thing for everybody, for our society. And I know that if you have this ratio here, that is this distance W divided by the horizontal length, and if this ratio is small, you have good results about the classical formulation. But you cannot have in real cases this small ratio, because this small ratio means that you need a very big, huge horizontal length. So you have a system like this one, and you cannot do that because you have some constraints. You don't have this space in your building. So this classical analytical formulation is not good for general case to assume as virtual experiment. But I was totally in love with this. Look, I ran this experiment with colleagues in Vienna, Professor Rudolf Hoyer, and you can see here this system that is excited. When you allow the liquid to move, the system, the real structure, is stopped, doesn't move. So this is amazing. This is great. And also, it's not expensive like the tuned mass damper. So I decided to go into details about the mathematical formulation. But I did a step backward. So I analyzed only the device, not the system and the device. So the device is here, and this is the classical formulation, the analytical one. And I ran experiments. As you can see here, during these experiments, I was very cared about the motion of this, the liquid inside. And you can see here that you don't have only this, with this flat surface, but the surface is inclined. There is a sloping surface. So this is the motion, goes up and down simultaneously with this inclined surface that is called sloshing. So you have vertical motion simultaneously acting with sloshing, so this changing of the horizontal surface. And the classical formulation doesn't take into account the sloshing. So we have to add something to take into account this sloshing. And here it's clear that you have sloshing. Look at this inclined surface. So, and this sloshing affects the frequency. The frequency of the system is different from the measured one. That's why the experimental results are totally different. That is the real world, by the way, are totally different from the numerical simulation. So I did a lot of experimental investigations, changing the geometry of the tube, everything. And then I was thinking, what about if I replace this term, that is with the integer order derivative. See here, this dot means derivative of order 1. And I replace this term with a fractional order derivative. So look, just something about fractional calculus. Don't worry, don't abandon me. I just tell you some few words, don't worry. So I just like to tell you that engineers are Euclidean. Maybe the humanists are less Euclidean than the engineers, in my opinion. So for engineer, it exists a point, a line, a surface, a volume, nothing between one each other. So the dimension is like 0, 1, 2, 3, nothing in between. And also the derivative, they are just integer order for engineer. They don't like this fractional order of derivative. But it was like fractional calculus was born in 1695, when the hospital asked Leibniz, what if the order of derivative is 1/2? And Leibniz replied, it will lead to a paradox from which one day useful consequences will be drawn. And he was right, by the way, he was right. So look at here, I put this fractional derivative term and I was astonished. It's amazing. Look, here you have the solid line, black and pink, they are experimental and the proposed method, they match very well. And the blue is the numerical one with the classical formulation that is away. So believe me, it was an heart attack because I succeed. Since I change everything, the geometry, I change the excitation all the time with this fractional term. Everything was matching very well. I was totally amazed. Believe me, I got lost my brain. Could be, of course, no more frustration at all. And so I consider also the system with this tuned liquid column device. So here is the classical formulation, and here is the proposed formulation, where I substitute this integer order 1 with this fractional derivative order beta, that is like 0.5, 0.8, it depends. So I did a huge experimental investigation. And of course, I match the results with the experimental black line, the classical formulation, blue line, dashed blue line, and the proposed fractional model that is red dashed lines. So, and as here you can see, in any case, in resonance, changing geometry, changing the frequency, changing everything where you like. In any case, you had very good results. You match the experimental results with our proposed model, and you don't match the experimental results with the classical formulation. So I propose all the investigation that I showed you before when I felt frustrated. So this is the first look, amazing. Look at here, it's like this, I don't know if you know that Tom Cruise had a new series, because this was before and this after. Like before fractional term, no match. After fractional term, a good match. So in any case, changing frequency, changing the length of the tube, changing whatever you like, even for Tolmezzo case that you saw before, and we say that is quite good, but now it's perfect. So I think, my dear friends, that I succeed in this way to find out a virtual experiment. So now, if you have this or this, it's the same. So now let's just do the concluding remarks. Experimental tests make the difference between mathematical method and scientific method. It's not easy performing tests, especially for validating a novel theoretical model. However, refining a theoretical model through tests allows you to perform virtual experiments, leading to tremendous cost savings and improved quality. The classical formulation of TLCD, tuned liquid column damper, allows us to predict the effectiveness of the control, but in some cases, it is not able to provide a good experimental numerical agreement. An alternative formulation has been proposed to better match the experimental results and to provide a virtual experimental example. So welcome this virtual experiment. And I hope that it will be the last step of the scientific method. So
now we can actually open up for discussion and the questions.
First of all, I like to tell you that the classical formulation, here you are, the classical formulation is this, and this term is nonlinear. So this is a nonlinear formulation, nonlinear differential equation. And when you replace this with the fractional derivative term, remember that the fractional derivative is linear. So this is a linear model, and this is a nonlinear model. So first of all, I check this, and I try to linearize the system to understand if I can be right or not, because if the system is strongly nonlinear, of course you cannot do that. And look, here is the nonlinear system solution, and this is the linearized one. So they match. So first of all, yes, I can think. But the best thing that pushed me to think, well, I put some fractional derivative term, because you are right. Generally, fractional derivative is used to talk about viscoelasticity, because they can capture, if you like, then we can share these comments, because viscoelasticity is the sum of a creep and relaxation. And if you have the fractional term, you can have only one real model. If you don't have this, you have two models, one for creep and the other one for relaxation. That is crazy. Believe me, it's crazy. By the way, but nobody used the fractional derivative term to capture sloshing, because when you put some fractional derivative term, affects both stiffness and damping. So it changes the natural frequency. So this was put in my mind. I say, the system with sloshing has another frequency. So if you put inside the fractional derivative term, it changes the frequency. Look, here is with the beta that is here, the fractional order of the derivative. Beta is equal to 1. Then 1.05, 1.132, and so on. You see, the system, the main frequency is changing, is going towards on the right. Can you see this, right? So this was, I think, well, maybe I will try, why not? And so I was very, very happy. I cannot say lucky, because of course there are a lot of study, but in some sense I was lucky, of course, as well. Believe me, fractional derivative term is like just a convolution integral. It's not a big deal, but it can capture a lot of real things, viscoelasticity, non-local terms, and in this case, sloshing, a lot. And in stochastic fields, a lot of help about using these fractional moments. But if you like, we can discuss together.
Interesting. Thank you.
You're welcome.
Thank you, Professor Pirrotta, this exciting talk and very interesting presentation. We're also very glad to have you here in Karlsruhe as the International Excellence Fellow. Yes, enjoy the sunny weather.
Danke for your consideration. I'm very grateful to you. I'm very touched to be here, and I am here in Karlsruhe, and I feel at home. So, danke to everybody. I feel at home, especially in these sunny days, and hopefully I don't get bored you, and I did my best. Thank you very much. Stay safe.